Welcome back. Today we'll look at paper 13 again from May-June 2025, and this is the IGCSE and O-level paper. Now, as always, as well as watching these videos, I will also recommend checking the mark scheme just to see the full list of answers. And of course, if the video is too slow, then you can watch at 1.5 or 2 times the speed. Okay, so question 1, a student records himself singing a song for his music project. The recorded sound is converted to binary to be processed by a computer. We want to give one input device the student can use to record the song. Okay, so I think this one's quite easy. Really, there's only one possible device we can say. Of course, yeah, that's going to be a microphone. Right, okay, then we want to, B, right, the student uses sound editing software to edit the recorded sound. We want to take one box to show whether the sound editing software is an example of application security system or utility software. So let's sort of go through these one by one. Right now, so application software. That's basically going to be software that the end user will directly use. So things like web browsers, let's say games, I guess office software, right? So yeah, sort of, Word documents, PowerPoint, Excel, all of that. I guess, I don't know, something like Notepad, right? This can also be, for example, so I guess, video editing software, right? Of course, sound editing software. So I think, here then, right, that's going to be application software, sound editing. Right, but if we just go through all of them, so security software. Now, usually this will be built into the operating system itself. So, for example, when you log in, of course, you have to enter your password. Right, well, of course, there's software that's, associated with, of course, storing your password securely, right, probably encrypting it, I guess hashing it. Right, also maybe something like biometric, if there's any sort of biometric security features, right, that's going to be security software. Any kind of two-factor authentication. I guess some things, for example, like cryptocurrency, right, you can get the hardware token. So, you would plug in some USB, and this USB would kind of verify that you're the owner of this wallet. So, I guess that's also going to be considered security software. So actually, I guess another good one is also firewall. Now, you might be thinking, say, antivirus, although generally they consider antivirus as utility. Although, probably, you can really consider antivirus as being both, right, utility and security. Right, then if we go to C, so system software. Alright, so really this can be anything that's kind of built into the operating system by default. So all the things about file management, memory management, I guess about security management. So some of these are kind of overlapping. Resource management, right, process management. Kind of all of those sort of built-in management tasks. Right, now this can also be other things, so it doesn't necessarily just have to be built in, right, it could also be something you download. So for example, I think in the book they list compilers, interpreters, linkers, anything sort of to do with programming, right, that can also be considered system software. Right, then if we say utility software, basically this is kind of extra software that's going to help with the performance, let's say maybe performance, maintenance, and organization of the operating system. So this can include things like the disk defragmenter. So if you've got a hard drive, then of course some of your files can become split up, right? They can become fragmented because let's say you have, I don't know, some large video, right? Maybe 10 gigabytes. Well, if you don't have like 10 gigabytes of contiguous, right, so consecutive space, actually on the hard drive, well, then that video has to be split up. Now, of course, when you then access that, well, now it's going to be slow because basically the read-write head on the hard drive, right, has to keep moving around. Just going to the different sectors, right, the sort of different blocks on the hard drive, when it's reading that file. So what a defragmenter is going to do, basically, it's going to rearrange all of the blocks, just so it can kind of like group the files together. Then you wouldn't have one file that's, separated, right? Basically that file. That file is going to be rearranged so it's stored contiguously. I guess other things can be like disk checkers, right? So checking you don't have any corrupted files or corrupted hard drive. This can also be, screensavers, they say. I guess antivirus, right? That's of course also included. I guess things like the disk formatter. So if, for example, you get a new device and you want to change the file format. So let's say, for example, you want to go, maybe from the FAT file system, right, so file allocation table, to, for example, NTFS. yeah, so I guess what the Windows NT file system. Alright, so yeah, basically kind of reformatting different drives. Alright, that can also be included. Yeah, so I think that's sort of most of the utility software. Right, okay, then C, so two binary numbers stored from the recording, right, well this, and we want to convert the two binary numbers to denary numbers. Okay, so I guess, yeah, if you want, you can of course write out the positional values. So I guess, yeah, 1, right, 2. I mean, it's quite difficult to do here because of course there's not too much space. Yeah, so of course, well, 1, 2, 4, 8, 16, right, 32, 64, and then I guess, yeah, 1 to 8. Now, I think here, because it's not said that they're using 2's complement, then we can probably assume that this is going to be unsigned. Okay, so just positive only. Right, that's why we have 128, not minus 128. Alright, so if we look at this one, well, this is 16, right, this is 8, that's 24, and then that's 1, alright, so that's going to be 25. Alright, and I guess, yeah, probably you might want to show your workings here. So of course, well, yeah, 16, right, plus 8 plus 1, right, equals 25. If we look at the next one, so well, that's going to be 1 to 8, right, plus 32, that's 160, right, plus 16, that's 176, and yeah, I guess plus 4, alright, that's going to be 180. Yeah, so I mean, hopefully I've not made a mistake there. Right, then the next one, we want to convert the two binary numbers to hexadecimal numbers. And actually this one is, well, yeah, okay, this one is easier. Now, some people, they sort of, okay, well, alright, yeah, I'm not going to say make a mistake because it's not technically wrong. But some people, they would go from binary, right, then to base 10, so, you know, to denary, right, then, of course, from denary back to hexadecimal. But, okay, yeah, so there's kind of two problems with that, right? One, I guess because you're doing two things, right, you actually now have two places you can make a mistake. Yeah, and of course it's just more complex, right, having to do this kind of extra conversion. Alright, so instead what we have to realise is that, well, because 2 to the power of 4 equals 16, then what that means is, well, 4 bits is going to equal to 1 hexadecimal character. So we can then split this in groups of 4. In fact, hang on, let's just try and draw that in the middle, right, between the ones. Okay, there we go. Okay, so if we look at the first group, of course, well, here then that's just going to be 1, right, so, well, obviously, yeah, no 8s, no 4s, no 2s, right, but there is a 1, so that's just a 1. Right, then if we look at the next one, so here we've got an 8, here we've got a 1, right, that's going to be 9. Then if we just do the same thing here, right, okay, so here this is an 8, that's a 2, right, that's a 1, so that's going to be 11, but of course in hexadecimal, well, 11 is going to be B, right, since A is 10, right, therefore B is 11. Right, then if we look at this, well, of course, right, that's just going to be 4. Right, then 3, so a logical right shift to 2 places is performed on the binary number. Alright, okay, that. We want to give the binary number that would be stored after the logical shift has taken place. Right, okay, so if we think, well, right shift 2 places, then, okay, yeah, so there's kind of a few ways we could do it. Right, either we could think, okay, well, that's going to go to, right, you know, this one is going to go to, this one's going to go to. However, I think if you shift them individually, I mean, honestly, like, that's kind of more complex, and it also takes maybe a longer time. Alright, so there's actually a simple way to do that. If we're shifting 2 places to the right, well, basically then we can just, you know, delete these rightmost 2, or yeah, we can, well, remove these 2 least significant bits, because of course they're going to get shifted out. And then if we think, well, from the left, we're then going to shift in 2 zeros. Right, so now, okay, yeah, so now this is just going to be our final answer. So it's just going to be, what, 0, 0. Yeah, let's make sure to write this down correctly. Yeah, okay, and that's going to be 8 bits. Alright, so hopefully that makes sense what I've done there, that because we're shifting 2 places to the right, well, therefore we can just, well, sort of, yeah, remove those rightmost 2 bits, and then of course just, you know, add in 2 bits coming in from the left. Alright, and of course if we're shifting, yeah, okay, right, if we're shifting from the right, so if we're doing a left shift, well, then of course, well, yeah, okay, right, then of course we would remove these left 2 bits, and then of course, you know, write in 2 zeros coming in from the right, yeah, if we were doing a left shift, or a, well, logical left shift. Right, then D, the 2's complement 8-bit binary integer, right, this is also stored. We want to convert the 2's complement 8-bit binary integer to denary, and again, we'll show all of our working. So here again, we can just write out the positional values if we want. Now, I guess let's just start from the right. So yeah, of course, 1, 2, 4, right, 8, 16, 32, right, 64. And then, of course, in this case, since this is 2's complement, well, the most significant bit is then going to be negative. So if we think here, and yeah, I mean, right, okay, honestly, like, this is probably overkill. I mean, I wouldn't really do this. However, I think for, yeah, okay, right, so some people, they actually like writing it all out. Right, so what we can then do, I mean, we can then just do an addition. So, of course, well, minus 1 to 8, yeah, plus 64, right, plus 8, plus 1. And then I guess if we do that, and in fact, what I'm going to do, I'm just going to do these first. So right, 64 plus 8 plus 1, that's going to be what, 73. So then we've got minus 128 plus 73. So if we plus the 3, that gets us to minus 125. Then if we plus the 70, what that gets us to minus 50. Yeah, okay, right, that gets us to minus 55. Yeah, I think that's fine. Yeah, alright, and then I guess probably we can just write minus 55 there, right, just to show us doing that calculation. Right then, E, the table contains terms and descriptions about the process of converting analog sound to binary. We want to complete the table with the missing term and descriptions. Right, okay, so this is the measurement of the height, right, or amplitude of a sound wave taken at regular time intervals. Right, okay, so what that's going to say, and yeah, maybe I'll just try and draw this quickly. Alright, so let's say we have, I don't know, some sort of sine wave, right, some sound wave like this. Then let's say we're going to sample here, I guess, and in fact, let's use a different colour just so we can see it. Right, okay, yeah, so let's say we sample here at, you know, sort of 0 time, right, then we have to sample here again, we sample here again, right, sample again. Okay, so what this is going to be yeah, alright, and I guess probably, you know, okay, yeah, so because this is digital, you can kind of draw the amplitudes like this, right? Yeah, okay, yeah, okay, because if it's digital, you know, we're not going to get that perfect sine wave reconstruction. We're of course going to get some sort of quantization error. Like maybe, for example, here we've actually sort of stored it as this, right? And then, yeah, okay, for example, okay, so maybe the next one we've stored here, yeah, because of, you know, the quantization error, because we can't represent, you know, every single value exactly, because we only have a limited sampling resolution. Yeah, okay, so what I kind of mean by that is, let's say, for example, here, well, let's say this value is 0, right, this value is 1, this is 2, this is 3, this is 4, yeah, obviously, etc. But let's say, for example, we have something here, well, this is 2.5, but we actually can't represent 2.5, right, therefore, that 2.5, for example, here, well, that would then have to get rounded up to 3. Yeah, likewise, if we have, I don't know, obviously, say here, like 4.2, well, again, 4.2 is going to have to get rounded down to 4. Alright, so that's going to give us a quantization error of basically 0.2, because the real value was of course 4.2, right? However, the value that we've actually stored digitally is going to be 4, right? Therefore, we've got this quantization error of, well, 0.2. Yeah, so hopefully that kind of makes sense. Alright, anyway, so yeah, the process of actually doing this then, right, the process of recording, I guess that's going to be sampling. However, if here they're talking about the actual specific measurements, right, the individual measurements, well then I guess we can just say sample. Yeah, that's what that's going to be. Alright, and I think for this one, let's type it, because yeah, my handwriting is not too good. Right, so the sample rate or sampling rate, this is basically the number of samples taken per second or per unit time. So I think we can just say that. Yeah, the number right, of yeah, okay, samples, let's say taken per unit time, right, e.g. per second. Yeah, I mean that should be okay. Right, then the sampling resolution, so this is kind of what I was saying here about on the y-axis. Right, so the sampling resolution determines how many bits we have to represent each sample, or well, how many bits we can use to store each sample. So let's say that, let's say, yeah, the number of bits used to store each sample. Yeah, I mean, we don't really have to say more than that, because I guess we just need the yeah, we just need the description. I guess if we want to be sure to get the marks, we could say, I don't know, yeah, maybe increasing. Right, let's say, yeah, increasing will. Well, I guess, well, that's going to increase the sound quality. And I guess in brackets, okay, right, the reason is because we're going to reduce the quantization error. Right, but let's say, yeah, however, right, however, the file size, right, file size will also increase. Yeah, and I guess we can also say that for the sampling rate, alright, it's kind of the same thing, where if we increase the sampling rate, well, the sound quality or the kind of sound accuracy will increase. So when we say accuracy, we mean the digital sound that we're storing will be closer to the original analog sound that was obviously played. Yeah, right, therefore we're reducing the quantization error. However, again, right, of course, the file size will increase because we're storing more samples each second. Yeah, so hopefully that kind of makes sense. Then question 2 says, a company employee is editing a video for the company's website. Data is stored in the random access memory or RAM when the video is edited. the RAM becomes full and the pages of data are transmitted to a partition section of the secondary storage to stop the computer from crashing. Right, and we want to give the name of the partition section of the secondary storage that's used in this process. Okay, so hopefully people know, right, this is just going to be virtual memory. Alright, and I think, yeah, I'll probably just explain how this works. Right here, yeah, virtual memory. Right, I guess I can probably draw it here. Right, so let's say here, this is our RAM. Yeah, okay, right, and of course with this RAM, as I said, right, this is going to be split into pages. Now, each of these pages, I think on Windows, again, it's just, well, 4 kilobytes, right, so the pages are quite small. If we think that our RAM is, I don't know, maybe, well, 16 gigabytes, right, could be 8, could be 32. I guess if you've got, I know, some, like, gaming, yeah, I know, some, you know, gaming laptop or, yeah, sort of specialist desktop, could even be 64 or 128 gigabytes. Okay, right, yeah, but basically then, well, that RAM, that's split into these 4 kilobyte pages. So in reality, you're going to have, I don't know, maybe hundreds of thousands, right, millions of pages. Now, if this becomes full, then we can't really have a situation where, you know, we then can't load anything else into RAM, right? Because, you know, well, then your computer is just going to stop working. You're not going to be able to do anything. So what we then need, we need to use secondary storage as basically a temporary, temporary storage area for the things in RAM that we don't currently need. So let's say, for example, this one here, yeah, okay, right, this page. Now, if, let's say, I know this is just some idle process, right, we're not currently using it, well, then we can then just, you know, temporarily move this into the virtual the virtual memory area, yeah, in our secondary storage. Likewise, okay, let's say this one, right, we also don't need. Right, so what we would do is, yeah, all of these unused pages we don't need, well, we can put them into virtual memory. Right, then, for example, as we're editing the video, I guess, yeah, if we're needing more and more memory, well, let's say, yeah, okay, right, okay, so this kind of new, I guess, part of the video that we're editing that we need to store in RAM, well, now, of course, we can then move it into this unused page. Yeah, likewise, of course, if we have another one, of course, yeah, we can then, you know, sort of, well, put this here. Alright, however, of course, at some point, you know, we're probably going to need these pages back from virtual memory, right, from secondary storage, of course, yeah, back into RAM. So let's say now, for example, yeah, okay, right, so maybe this page is, like, not needed. Well, then, of course, we can move this page here, yeah, into our virtual memory, right, and then this page that we originally moved, well, then, of course, we can then move this back, yeah, into this, you know, sort of page that's become available. Alright, so hopefully that makes sense what we're using virtual memory for. Just to temporarily store pages, yeah, that are kind of unused if the RAM has become full. Alright, and then, yeah, I guess B, so the secondary storage is a hard disk drive HDD. Right, an HDD is an example of magnetic storage. One feature of magnetic storage is that it uses platters, and we want to give 3 other features of magnetic storage. Okay, so I guess what we can say, maybe we can say what the platters will spin. Yeah, or I guess the hard drive is moving. Okay, let's say that, right, the hard drive, okay, yeah, so here I guess it's talking about magnetic storage generally. Right, so let's say magnetic storage uses moving parts, right, e.g., I know, yeah, e.g. spinning platter, I guess, well, moving read-write head, right, let's say, etc. Right, I guess, yeah, 2, and I mean, right, okay, so this one is kind of the same as number 1. I think number 1 we've probably maybe mentioned 2 things there. So I think, yeah, let's mention about the read-write head again. Let's say maybe a read-write head, right, with an electromagnet. Let's say what moves. Yeah, I don't know, like moves kind of like in and out, or like to different sectors. Let's say, yeah, 2 different sectors, right, of the disk. Let's say, yeah, and I don't know, yeah, and can read-write data. Can read-write data, right, based on the magnetism. Yeah, I guess that's okay. All right, and then I think for 3, maybe we can mention how the data is actually stored. So basically, it's going to be what the polarity. Yeah, okay, yeah, alright, so I think actually there's 2 ways. So either it can be the polarity, right, or it can be basically whether it's magnetized or not magnetized. So let's try and say this. Let's say maybe, yeah, bits can be represented. Right, bits can be represented, let's say, right, based on either the polarity. Let's say the polarity, I don't know, yeah, of that sec. Okay, right, okay, yeah, all right. And when we say polarity, let's just say what that means. Let's say, I don't know, yeah, north or south. So yeah, I guess whether that, whether that part of the disk is charged, right, north or south. Right, let's say the polarity, or I guess maybe the magnetism level. Right, the magnetism level, right, of that particular part of the disk. Yeah, I think that should be okay. Right, okay, then C, we want to give the reasons. Yeah, okay, so I guess multiple reasons. Right, why HDD hard drive is an example of secondary storage. Right, so secondary storage, I think there's two requirements. Right, one, it can't be directly accessed by the CPU. So if we have data, let's say, from a hard drive, first it has to be loaded into the RAM, right, then from the RAM, right, then it goes to the CPU. Likewise, if we're saving data, or I guess if we're writing data, first it's going to go from the CPU, right, then it goes to RAM, and then, from RAM, right, then it can be written, to the hard drive. Alright, yeah, okay, yeah, alright, so actually, let's just say why it does that. Now, the reason it does that is because basically the hard drive is going to be extremely slow, or I guess any secondary storage, right, even SSDs, right, they're going to be extremely slow compared to the CPU. So we wouldn't want a situation where, let's say, the CPU wants to read data, and you have to read that sort of kind of like in real time from the hard drive. Alright, so instead what you'd want to do, you would want to preload that from the hard drive, obviously preload it into RAM, right, then of course from RAM, then that's going to be much faster for the CPU to load it. And in reality, actually, it's probably going to be preloaded or prefetched, from RAM and actually stored in the cache as well. If it's kind of like detected as being needed, sort of kind of in the immediate future. Right, so let's kind of say that. So I guess it can't. Right, okay, yeah, let's say the HDD can't be directly accessed. Right, directly accessed. Right, by the CPU. I guess we can mention about reading and writing. Okay, let's say I don't know, to read-write data. Let's say from to the HDD. Let's say first, the data has to go via the RAM, as an intermediate. Let's say that right, the data has to go via RAM, right, as an intermediate. I know, okay, yeah, all right. So maybe intermediate stage, right, or intermediate storage. All right, so I think probably that's going to be one point. Right, then the second point, we can say the secondary storage is going to be non-volatile. So when we turn off the power, right, the data is not actually lost. Right, let's say also, right, let's say an HDD, right, is non-volatile. Right, let's put in brackets. Right, so meaning, right, meaning data. I guess data is permanent. Okay, right, let's say data is stored. Right, data is stored permanently. I think that's spelled wrong. Or no, I guess right, maybe not. Right, so data is stored permanently. Right, / not lost when the power is turned off. Okay, right, and I guess we should say that obviously being non-volatile is a property of secondary storage. Right, let's say that which is a property, right, of secondary storage. Because I guess otherwise saying it's non-volatile, I guess that's true, but like, how does that relate to secondary storage? Alright, so I think saying that, I guess non-volatile is a property of secondary storage, that just kind of ties things together right back into the question. Then question 3, a computer with a von Neumann architecture has several hardware components. Right, we want to complete the table with the missing terms and descriptions about computer hardware. Right, so the first one, this is the address given to a network interface card or NIC when it's manufactured. Right, okay, so talking about an address, and again, this is kind of hard-coded in the factory, right, therefore we can't change it. Well, and to be honest, right, this is kind of weird because it doesn't really relate to von Neumann, because, von Neumann really is talking more about kind of executing instructions, things like the stored program concept, right, of course, saying, well, the, okay, right, so both programs and data are both stored in RAM, or both stored in memory. And then, of course, talking about the actual internal operation of the CPU. right? So things like the program counter, the MAR, the MDR, CIR, yeah, just talking about all of that. Whereas to be honest, I mean, right, yeah, okay, so this first one is really about networking. Alright, so thinking about the address that's actually hard-coded, well, that's going to be the MAC address. Right, of course, an IP address, well, that's going to change, right? That can be dynamic. Yeah, although even if it's static, right, it's still not actually hard-coded into the actual hardware itself. Yeah, of course, even if it's static, right, it's still going to be assigned, it can still change. Yeah, okay, right, and actually, I guess if you want to see this, let's say if you're on Windows, then, well, of course, you can just open command prompt, right, PowerShell. I guess also if you just go into your Wi-Fi settings, and then I think if you just type in ipconfig/all, of course, yeah, okay, yeah, there's also a space here, right? But then you can see, well, your MAC address, your IP address, yeah, your DNS server, DHCP, yeah, kind of all of those network properties. Right, anyway, so the next one, register. So I guess we can say what is a small temporary fast access memory inside the CPU. And it can be used, I guess, to store data, store addresses, or store instructions. Yeah, let's try and say that. Let's say a small, a small temporary, very fast access. I guess I don't know, yeah, memory. Let's say I don't know, memory store, right inside the CPU. Yeah, or I guess actually, okay, let's say inside the cores. Because if we have multiple cores, well, then we have multiple copies of the same register. So, for example, let's say we've got 4 cores. Well, then each core is going to have its own program counter, right? Each core has its own MAR, MDR, CIR, yeah, index register, status register, etc. Yeah, I guess also like ALU, control unit, right? So all of those are going to be independent, right, for each core. Yeah, so a small temporary fast access memory store inside the cores. Yeah, I think that's fine. Let's see what it stores. Right, maybe can store. I know, yeah, data, instructions, and addresses. Yeah, I think that's probably going to be okay. Right then, if we say the clock, so this is used to synchronize the CPU components, or just rather, yeah, the computer components generally. And we say that on each clock tick, a new fetch, decode, execute cycle will start. Yeah, I think let's say that, right, used to, yeah, let's try and spell this correctly. All right, so synchronize. Well, let's say the CPU, or yeah, I guess the CPU components. Right, synchronize the CPU components. Yeah, right. Then let's mention about the clock tick. Right, let's say yeah, on each clock tick. Right, a new. Okay, right. So yeah, okay. Probably we can just write FDE. Although I think it's probably better to write it out in full. Right, fetch, decode, execute cycle. Yeah, will start. Yeah, again, I think that should be good enough. Right, then if we say the control unit, so the main function of the control unit is to decode the instructions. We can also say it's going to manage the components inside the CPU. Yeah, and I guess you could also mention that it's going to contain the system clock. Yeah, and also, things that handle interrupts as well. Right, so let's kind of do that. Right, okay, let's say maybe handles. Right, handles decoding of instructions. Right, so handles decoding of instructions. Maybe let's say manages data flow. Right, let's say and assigns. Let's say okay, all right. So rather than going assigns, let's say maybe send signals to, I guess, I don't know, different components, telling them to execute specific instructions, something like that. Right, let's say send signals. I guess, I don't know, to other components. Let's say responsible, right, for executing that particular instruction. Right, yeah, and I think here let's give an example, right, so e.g., let's say, I don't know, right, okay, yeah, so let's say the ALU, right, will execute the add instruction. Okay, so what I mean by that is, let's say if we've decoded the instruction and it turns out that it's going to be an add instruction, well, then the control unit will send a signal to the ALU, basically telling it to, sort of perform this addition. If, for example, we find it's an LDD, right, if it's a load instruction, well, then it will send a signal, I guess, on the, yeah, okay, right, so one, it will send the read signal, right, on the control bus. Of course, it's also going to send the address signal, Yeah, okay, right. So the address signal which we're reading from on the address bus, and of course that address will have been previously stored in the MAR. Right. So from the MAR, it's going to be then sent on the. Okay, yeah, sorry. Okay, so from the MAR, it will be sent on the address bus, and then it will be intercepted by the different memory components. So, for example, well, first it will go to cache. Now, let's say we want to read from, I don't know, like address number 1000. Well, if we say that cache only has addresses from 0 to 500, well, then of course cache realizes that, you know, this address is not meant for it, right? So that, okay, then it's going to continue on the address bus, right? Then it's going to reach RAM. And of course, well, RAM is going to look at it, and let's say RAM has the addresses, I don't know, like 501, right, up until, let's say, like, you know, sort of 1 million or 1 billion, right? Well, because that's in the range, then of course RAM knows that it contains this address, right? Therefore RAM will basically, well, look, you know, sort of inside the RAM itself, right? It will then load the data from that address, right? Then it will send that data back on the data bus, and of course, yeah, that will then be stored in the MDR, right, when it arrives back in the core. Alright, so then if we say the final one, so this is a processing unit within the CPU that can fetch, decode, and execute instructions. So I think actually this is the exact same as paper one, right? So if you've looked at paper one, right, then you should remember that's going to be a core. Yeah, and I guess that, you know, this one's actually a bit tricky. Yeah, because okay, yeah. So here it's saying it can obviously do all of them, right? Fetch, decode, and execute. And again, the reason it's a core is because, as we've said, well, the core is going to contain basically a copy of everything. Right, so let's say if yeah, okay, right. So again, thinking about like registers. Now, of course, a core is going to have its own, well, its own program counter, its own MAR, its own, right, MDR, CIR, etc. Again, it's going to have its own control unit. It's going to have its own system clock, right? Of course, that's inside the control unit. It's going to have its own ALU, right? Just etc. Right, then we want to identify 3 registers that are using the fetch stage of the fetch, decode, execute cycle. Right, so I think here, you know, we can probably mention, I guess, yeah, let's try and mention all of them. Right, so of course, well, the first one's going to be the program counter. Alright, I guess we can just say PC. Right, okay, the next one, so from the program counter, well, we say that address is then copied into the, well, the MAR, right, the memory address register. Right, of course, yeah, MAR. Right, okay, so then from that, well, then we're going to load the data, or well, load the instruction at that address. Right, that instruction is then copied into the MDR. Right, so yeah, memory data register. Right, MDR. Right, okay, yeah, so then when we have that, well, that instruction is then copied into the current instruction register. Yeah, or of course, well, CIR. Yeah, alright, so hopefully that makes sense. And if you're not familiar with the fetch, decode, execute cycle, I would say, yeah, just recap that, right? Make sure you understand each stage kind of thoroughly. Of course, you can also use my site, right? Well, yeah, asmcode.pro, right? That's going to kind of demonstrate that visually. But yeah, I guess otherwise, you know, just obviously, well, search videos on YouTube. I know, yeah, ask, right, ChatGPT, yeah, sort of look, you know, look in the book, whatever. Right, then C, we want to circle the 2 buses that are used in the fetch stage of the, well, yeah, fetch, decode, execute cycle. Now, actually, this question is a bit weird because in reality, actually, all of the buses are used in the fetch, well, yeah, in the fetch stage. However, I guess here they've only listed 2 of them. Right, so just looking for the 2 buses, well, of course, right, that's going to be the control bus, and then, yeah, also the data bus. Right, so, yeah, okay, right, let's actually think kind of what's then sent, yeah, on these buses, right, during the fetch stage. Right, so of course, well, okay, during the fetch, well, that means we're basically loading the instruction, right? We're sort of reading the instruction from memory. Okay, so what's going to happen? All right, and I'm just going to write these here. So let's say on the address bus, right, then we've got, well, the data bus, right? We've also got the control bus. Right here, we're going to have RAM. And let's say here, yeah, okay, right, so this is the CPU. Right, okay, so of course, in the CPU, well, we've also got the MAR. Right, we've also got, well, the MDR. Right, so these are going to be the components that are required, yeah, for the actual, well, fetching of the instruction itself. Right, so let's say in the let's say in the MAR, I know we have the address number 100, right, and of course, yeah, that's all going to be inside the processor. Right, so what's going to happen then is, well, that 100 is going to be put on the address bus. So yeah, let's just sort of write that here, right, and I guess also we need the control unit as well. Right, so because we're fetching, well, fetching means we're reading from memory. So basically there's going to be, I guess, well, 2 possible outcomes, right? So either we can read, right, or we can write. Now, let's just say, for example, okay, yeah, all right. So let's just say, I know, like, yeah, okay, right. So let's say read is, you know, the sort of bit 0, and if we want a write signal, that's going to be the bit value 1. So because we're reading, well, that means then we're going to send a 0 right on the control bus. And yeah, so actually at this point we actually don't need to send anything on the data bus, right, since we're just reading. Alright, so as mentioned, what's going to happen? Well, basically RAM is going to get this. It's then going to look, right, it's going to see, well, what's actually the value in address 100, right, and let's just say, I don't know, this has some instruction. Let's say like add 5, for example. Okay. So what's going to happen, once we've read that, well then this instruction, right, this add 5, right, this is then going to be sent back right on the data bus. Okay, and of course, yeah, so what's going to happen, well, once that arrives back in the CPU, or yeah, back in the core, well then of course that's going to be put here in the in the MDR. Alright, so yeah, now the MDR is going to contain the add 5, of course, right, that's then going to be copied into the CIR, right, etc. Alright, so as we can see, actually all of the buses are needed. All of the buses are needed during the fetch stage. Right, of course, on the address bus, well, that's the address we're reading from. And of course, well, that came from the PC originally. Right, then of course that's copied into the MAR. Right, obviously on the control bus, well, we need to say, right, are we doing a read signal, are we doing a write signal? Then of course, well, the data bus, that's going to be used for sending the instruction back. That we've just read. Question 4 says a computer has an operating system. One function of the operating system is handling interrupts. We want to describe the role of the operating system in handling interrupts. Okay, so I guess we can mention what that each interrupt is assigned a priority. We say that if there's an interrupt in the priority queue, then basically the one with the highest priority is going to be the one that's executed first, or yeah, the one that's handled first. And the way it's handled is we say that the interrupt service routine, or in fact, actually, okay, right. So let's say the start address of the interrupt service routine is loaded into the program counter, right? Then of course that can be executed. So if we think the interrupt service routine is literally just code, just like any other executable program. Alright, and I guess we could also mention that before that happens, I mean, we've also got to store the current contents of the registers in RAM, because if we're executing some program, well, I guess after we've handled the interrupt, then we just need to sort of continue execution of that program, from the point it was currently at. Right, that's why we need to then save the current program counter, the current MAR, MDR, CIR, right, status registers, index registers, right, etc. Alright, however, I guess here we've only got 2 marks, so we obviously can't really say all of that. Alright, let's maybe sort of try and get the main things. So let's say, right, so how does it handle interrupts? Right, let's say, the OS, assigns priorities, priorities to all, I guess, incoming interrupts. Let's say, these are placed, in the interrupt queue. These are placed in the interrupt queue, and the interrupt, with the highest priority, let's say, will be handled first. Let's say, so what that means, right? Let's say, this means, let's say, the start address of the, so we could say ISR, right? However, I guess maybe we actually have to write the full name first. Let's say, of the interrupt service routine. ISR is loaded, into, loaded into the program counter. And what this interrupt is executed. I think that's fine, right? And then probably let's say what happens once it's finished. Right, so let's say once finished. I guess I know, like, sort of. So once finished, other interrupts are handled if they exist, right? Else the original program, or in fact, let's say else the contents of the registers of the original program are loaded back into RAM, right? And that program can, that process can resume execution. Let's say that, right? So once finished, let's say other interrupts, in the interrupt queue, are handled. Let's say else, if it's empty. Here we go. So if it's empty, the original, the original process, or in fact, let's say the original processes, I guess, register values, register values are, I guess, well, reloaded, or okay, let's say loaded back in, right, loaded back in, right, and okay, let's say and execution can continue from, I guess, what, from the like interrupted point. Yeah, okay, so honestly, like, this question is quite weird, because usually for this question they give about 5 or 6 marks. So, you know, figuring out what specific parts of those 5 or 6 marks they want, you know, when they're just given 2 marks here, yeah, it's maybe like a little bit tricky, right? That's why I've kind of gone overkill and, you know, just wrote all of that. Right, then the next one, so we want to give 2 other functions of an operating system. So I guess here we just think about the different management tasks. So for example, we can talk about memory management. Right, let's give memory management, and I guess let's say maybe file management. Right, yeah, okay, so if we try and think for all of them, so well, memory management, file management, I guess security management, process management. I mean, some of those, like process management, resource management, they sort of consider the same thing. You can also say it provides an interface. So yeah, like an interface for the human to interact with the hardware. Yeah, I guess things like that should be fine. Right, so then C, hardware and software interrupts are 2 types of interrupt, and we want to give 1 example of a hardware interrupt and 1 example of a software interrupt. Okay, so hardware interrupt, I mean, yeah, so you could mention, I don't know, some like, you know, broken hardware. However, like maybe that's a little bit vague. So we could also mention user input. So user input, right, let's say clicking the mouse, right, typing on the keyboard. Yeah, I mean like the sort of power off button, right, something like that. We can also mention, I guess, for example, yeah, okay, right, so one they often mention is printers. Let's say printer out of paper, printer out of ink, right, kind of something like that. Right, but I think, yeah, okay, right, let's probably just say that. Let's say, right, printer out, yeah, out of paper. Yeah, I think that should be fine. Right then, 1 example of a software interrupt. Again, there's many examples. I think, well, division by 0 is one they always say. You could probably say like array. Yeah, okay, right. Let's say array index out of bounds. So if you've got an array that goes, you know, 1 to 5, but if you try to access element 6, well, of course, element 6 or index 6 doesn't exist. Likewise, you can say the same for strings. If you've got a string with 5 characters, but you try to, yeah, if you try to access character 6, well, again, character 6 doesn't exist. You can also say maybe assigning invalid data types. So if you've got an integer but you try to assign it to a string, or if you try to do some invalid operation, right? Maybe, for example, you try and do a plus, right, between an integer and a string. Well, maybe that particular language doesn't support that operation. Alright, but I think okay, yeah, so let's just go with the obvious example they always use. Let's go, well, division by 0. Yeah, and let's sort of write 0 like that. Right, okay, then number 5, an online company has a website that allows their users to buy products. The user types in uniform resource locator URL, right, basically just the website name, you know, like google.com, right, for the website, and this is sent to a domain name server, or DNS, and we want to describe the role of the DNS. Okay, so I think let's just try and draw a quick diagram of this, just explaining how this works. Right, so if we're trying to go to a website, then I guess, yeah, let's just draw this here. Okay, so we're going to be the client. Now, what you have to remember is that generally, I mean, humans are not good at remembering numbers, so we can't remember IP addresses. However, if we think about the internet, well, the internet works based on IP addresses. I mean, yeah, like packet switching works based on IP addresses. Alright, because if we think basically with numbers, you know, we can basically kind of like easily categorize, you know, things into different locations based on numbers. Whereas, yeah, if we have text, I mean, it's much harder to make a routing protocol, you know, based on text, right? Yeah, okay. So that's what IP address is, you know, based on numbers. Right, but what we have to do then is, well, we have to convert, the domain name or the URL into the IP address. So that's where we're going to have the DNS server. All right, let's go, yeah, DNS server. So what this is going to have, basically, it's just going to have a list of IP addresses. So I don't know, let's say, yeah, one. In fact, let's probably do it the other way around. All right, because I guess really we're mapping the domain names onto the IP address rather than the other way around. Right, so let's say we have, I don't know, like google.com. Okay, right, so here we've got google.com. So this is, well, the domain name. Right, here then we've got the IP. And let's say, I know, google.com has the IP, you know, 1.2.3.4. Right, then we have some other website. I don't know, maybe this is, yeah, 2.3.4.5 or something. Obviously, other website, other IP, yeah, kind of, etc. Right, so, okay, yeah, basically this is just going to be a database containing the domain name's mapping to its corresponding IP address. So what's going to happen? Basically, we're going to send a request right to this DNS server. And actually, if for example you use something like Wireshark, so this is something I've mentioned before. Right, now Wireshark, this is a program which lets you basically check the packets that are coming in and out of your system. Alright, so if you see this in Wireshark, you can actually see the DNS request, and basically what it's going to be, it's just going to say, well, what is the IP address of google.com, right? That's kind of saying, that's kind of what's sent, right? Then what's going to happen, of course, well, this is going to look, right, it's then going to see this IP address, and of course, if it finds that, well, then it's going to be sent back, so then it's just going to send the IP address of this back. Now, the thing is, there's actually different stages of DNS, DNS is kind of hierarchical. So I think what we can actually say first is actually, well, first the client is also going to check, does it know the IP address? So if you're in a web browser, well, first you're going to check the web browser, right? If the web browser doesn't know the IP address, so the reason I say like the web browser might know is because like what happens is, let's say if we've gone to Google, and then let's say like 5 minutes later we also go to Google again. Well, the thing is, the web browser is going to temporarily store, or it's going to temporarily cache, right, the IP address for that particular website. And to be honest, it's actually not very long. I think it's only for like 1 minute. And the reason it's only for 1 minute is because, let's say if you have some DNS cache poisoning. So if, for example, rather than 1, 2, 3, 4, right, someone has like maliciously sent back 1.2.3.5. Well, if for example you save that for, I don't know, sort of 1 year or like permanently, well, then you'd be kind of permanently going to some malicious server that's claiming to be Google but is actually not. Whereas if instead they only save it for 1 minute, well, then in reality you're only going to be going to this malicious server for 1 minute, right? And then hopefully when you then do a DNS request again, well, hopefully now the DNS request is not going to be like intercepted, right, corrupted. So anyway, what's going to happen, right, is, well, first it's going to check the web browser. Of course, if the web browser knows, well, then it can just stop the DNS request. Right. However, if the web browser doesn't know, well, then it's going to check the operating system. Because inside the operating system you also have some DNS records. That's going to be in the host file if anyone wants to look at that. Alright, so if you're on Windows, you can just type in, right, where is the host file, and you can basically see, right, do you have any custom DNS records set. I think, for example, on Linux, right, Mac, that's going to be in etc, right, /hosts. You can just sort of cat that, right, just to output the contents of that file. So well, first you're going to check the web browser, right, then you check the operating system. If the operating system again doesn't know, well, then then you're going to check the router. Right, so the router also has its own DNS records, right? The router has its own sort of DNS server built in. If the router doesn't know, well, then it's going to go to the ISP's DNS server. And in fact, let's just say like router's DNS server. And finally, if the ISP, right, so the internet service provider, right, if the ISP's DNS server doesn't know, well, then it's going to go here, right? And so here I guess we can call it the global DNS server. I think actually they also call it the authoritative. So the I think there's another TA there. So the authoritative name server, and that's basically the collection of global name servers, or the global DNS servers that contain basically like the master records. And I think in the A-level book it says there's 13 of these worldwide. There's basically like 13 copies. Although I think so I think maybe that's out of date now. Like possibly there's 20 or something. Let's just try to explain this, and I guess it's only 2 marks, so we don't need a huge amount of detail. Although of course if for example it was a 6-mark question, well then you'd want to sort of try and explain some of the stuff that I've just mentioned. And in fact so what's the exact question for so describe the role of the DNS. Alright, so let's see it's used to convert a domain name into an IP address. So let's see that it's used to convert a domain name. Alright, and let's also mention why this is required. Right, let's say which is easy to remember for humans. Into an IP address. An IP address which is required. For I guess like routing. Routing in a packet switched network. Yeah, okay, right, let's say maybe, yeah, it's right, it's hierarchical. Right, it's yeah, hierarchical. Alright, yeah, I'm not really sure how to spell that. Right, so it's hierarchical, let's say, and different, right, different places, right, are checked to see, yeah, to see if they know the, well, I don't know, yeah, DNS record or IP address of that domain. Right, of that, yeah, I guess of that domain. Right, okay, let's say, yeah, e.g., I don't know, yeah, web browser, router, let's say, yeah, ISPs, right, ISPs DNS server. Yeah, okay, right, let's sort of say, right, so ISPs DNS server, right, and yeah, authoritative, right, authoritative name server. Yeah, alright, and I guess, you know, also operating system, although I didn't mention that because, yeah, we don't really have space there. Right, so is there anything else, right? So, okay, and actually, I think they often say it's a hierarchical database. Yeah, because, okay, yeah, so basically it's a database mapping the domain name to the IP address. Yeah, and sometimes they also say distributed, right? So it's a hierarchical distributed database. Alright, and the reason it's distributed is because, like I said, there's not just one global DNS server, right? There's actually, well, 13. Or again, you know, probably like now there's probably, you know, 20 or more. Yeah, and I guess you can also say it's distributed because, again, I mean, you don't just have the actual sort of, yeah, global DNS servers. I mean, you also have the routers, you have the ISPs, DNS servers, right, etc. But yeah, I think hopefully that should be enough there. Yeah, I mean, for 2 marks that should be fine. Right, so the next one, the website asks the user to input their username and password to log into their account. The company wants to make their login system more secure. Right, we want to take one box to show one other security method that could be added to make the login system more secure. Right, so again, let's talk about all of these individually. So access levels, this is basically just user permissions. So let's say you have some website, or it could be your operating system. Now, yeah, okay, right. So yeah, so let's think of a website example first. Now, if, for example, you have a school website, you might have different user types, right? So you have like an admin, you have a teacher, right? And then you have a student. So let's say, for example, the student, well, they can, I don't know, sort of, yeah, see their courses, they can submit their homework, right? Things like that. Yeah, probably they can send emails. Now, if we think the teacher account, well, the teacher account, let's say they can create new courses, right? They can create homework, right? They can sort of see the students' grades, yeah, in their, you know, in their homework, for example. Then of course, like an admin, well, they can, you know, create teachers, delete teachers, obviously, yeah, you know, create, add students, whatever. Alright, so hopefully that makes sense what access levels are. Basically just different permissions for different users, right? Different functionality for different users. Yeah, okay, right. And of course the reason that makes it more secure is, well, one, I guess if you have someone sort of inside the company or inside the school that's, you know, malicious. For example, you wouldn't want to give students access to, like, sort of delete other students because, well, of course, you know, then you'd have someone as a joke. Like they would just, you know, delete all the students in their class, for example. Okay, likewise, if an account gets hacked, well, if a student account gets hacked, you know, by some like outside, like, yeah, I know, some outside hacker, right, third party, you know, then actually the hacker is not going to be able to do that much, right? All they can do is, I don't know, just like submit some student's homework, which is not really that malicious. Whereas, for example, if let's say they hack an admin, well, then of course, yeah, they're going to have much more control, right? But that, okay, yeah, okay, that's why generally you're of course only going to have a small number of admins, right? Therefore, it's going to be less likely that you can hack them, you know, obviously compared to like thousands of students. Right, then we say a firewall, so basically that's going to look at all the incoming and outgoing packets. Then it will just decide whether to accept or reject them. Yeah, I guess based on some criteria. So, for example, based on based on the IP address, right, either the incoming or outgoing IP address, it can ban. Yeah, sort of things like based on the protocol. So maybe something like SSH. Okay, yeah, okay. So for example, SSH, right? That's going to, well, secure shell, right? Connecting to another server. Now, maybe you don't want people trying to connect to a server, you know, within your company, or therefore you can disable that protocol. Things like the port number, again, right? That's, well, generally going to be related to protocol. So I think SSH is maybe like 22. I think the port number for FTP, yeah, I think that's maybe 20 or 21. Right, so some of these protocols, I mean, you can block those port numbers to prevent people from, well, for example, trying to access FTP, right, file transfer protocol. So basically just trying to upload files, download files, right, if we want to prevent someone from doing that. Yeah, then if we say spyware, so of course this is going to be trying to steal user details, maybe like a keylogger, right, trying to steal their password, right, steal their username. I guess it could be something that's just, I don't know, just like looking at all the files on your system, right, sending it to the kind of, third-party server, right, therefore stealing all the files on your system. Yeah, I guess it could be, I don't know, like sort of looking through your webcam, taking screenshots, yeah, and any kind of spying behavior, right, yeah, sort of like listening to your microphone, right, stuff like that. All right, so I think really, yeah, okay, so if we think about all of these, I guess really like, okay, so access levels, I mean, that's not really about making the login more secure. That's kind of like after they've logged in, right? So that's kind of talking about once they've logged in, right, limiting the amount of stuff they can do. I mean, likewise, firewall, I mean, a firewall, I guess, can be used to kind of limit brute force attempts because, for example, if someone is sending on, 1,000 requests every second, well, that's probably suspicious, right? Therefore, you can block that IP address. I mean, likewise, spyware. I guess that can be used, let's say, to steal their login by, well, of course, like a keylogger, for example, right, recording their keystrokes. Yeah, although to be honest, actually, that's going to be a problem for the end user, right? So, for example, if the end user gets their account stolen, yeah, it's not really a problem for the company itself, right? If the end user gets their account stolen. All right, so I think probably therefore, yeah, the most obvious answer is going to be this one, right? Two-step verification. So of course, once the user successfully types in their username and password, well, then they're going to have, I don't know, some, let's say, yeah, some like SMS message, right? Maybe type in a 6-digit code sent to their, sent to their phone. Of course, it could be sent to their email. It could also be used on some app like like the Google Authenticator app. Again, yeah, that's going to be a time-based, right? Time-based two-step verification. Right, so then C, the company uses a proxy server to keep the web server safe from a distributed denial of service or DDoS attack. We want to complete the annotated diagram to show how a DDoS attack is carried out on the web server. Right, okay, so I think for these ones, what they usually have, they would have what the attacker. So let's sort of say this. Right, okay, let's say attacker. Or in fact, we can say what the attacker's, I guess, control server, or yeah, command and control server. Alright, let's say that, right, command and control server. Yeah, alright, let's sort of make that bigger. Okay, right, so then what this is going to be connected to, well, this will be connected to all of the bots in the botnet. So let's just sort of try and draw these. I know, well, let's say, yeah, like bots, right, I guess there's going to be another bot. Yeah, let's sort of do 3. Right, okay, so what we can say, let's say maybe, yeah, bots. Okay, alright, yeah. So when we say a bot, of course, right, that's just someone else's device, right? It can be their computer, it could be their phone. I don't know, it could be their, like, internet-enabled fridge. So let's say bots, let's say, yeah, unknowingly. Right, unknowingly, right, infected with malware. Right, what we can do, let's say signal, okay, yeah, so probably here, right, go into the bots. We can say what attacker sends signal for bots to attack. Yeah, let's say that, right, so attacker, right, sends signal, and in fact, yeah, let's say simultaneously, right, so attacker sends signal, right, for all bots. And yeah, okay, well, let's say what to attack or send requests. Right, send requests to, well, web server. Right, web server simultaneously. Alright, yeah, okay, and of course the reason it's going to send them simultaneously is because, well, then the web server is going to be overwhelmed by more traffic. So let's kind of sort of draw those. Yeah, I mean, probably get some arrows on this. I guess, I don't know, what, just like sending requests. Right, okay, and then what we can say, right, the web server, let's say maybe overwhelmed. Okay, yeah, overwhelmed, right, by too many malicious requests. Alright, and then I think often for these, they often have like a legitimate user as well. So let's sort of do this. Let's say, right, legitimate user. Right, and then let's try to sort of draw this. Right, let's say request. Right, and okay, yeah, so let's say maybe request can't be handled because the web server is kind of overwhelmed by the malicious requests. Yeah, let's say requests can't be handled. Yeah, well, okay, yeah, and alright, so I'm probably not going to write it, although you can probably just write this again in the exam. Yeah, because the web server is kind of overwhelmed by too many malicious requests. Alright, so yeah, hopefully that kind of makes sense. Right, then we want to identify two tasks that can be performed by a proxy server that are not performed by a firewall. Okay, so this one's a bit tricky. If we think then the difference between a proxy server and a firewall. Alright, so a proxy server is going to have its own IP. Okay, right, so it's its own IP address. Because basically the proxy server is kind of just like a completely independent device. Whereas if we think a firewall, now often a firewall is going to be built into the router, right? So that, okay, yeah, that's going to be a hardware firewall. You can also have a software firewall which is actually on your computer. Alright, so a software firewall, for example, in Windows. Now, if, for example, you just go into your Windows settings, right, of course, search firewall, well, you can add custom firewall rules. So, for example, blocking certain IP addresses. Again, yeah, blocking based on the port number. Right, blocking applications. Yeah, or even like allowing, certain applications through. Okay, so yeah, okay, what we say then is that the proxy is going to have its own kind of unique IP address. And the reason for that is because, well, again, basically it's like an independent device. Therefore, what we say is that the proxy can be used to hide the IP address, I guess, of the device that's sending the request, or of our device. So let's sort of say that. All right, let's say since the proxy will have its own IP address. Let's say then so then it can be used, right, to hide our IP address. I guess, I don't know, for privacy/security reasons. Right, I think that's fine. Yeah, then I guess if we talk about another one, I guess a proxy can also be used to cache. So yeah, just like temporarily saving the files that we visited, or the websites we visited. So let's say we visited some website, and of course, so when we visit that, well, the website's going to send back a load of information. Right, so one is going to send back HTML. Right, it's also going to send back CSS, JavaScript, right, images, videos, audio. Now, if, for example, we go to that website, I don't know, like sort of 1 second later, if we just like open up another page on the same site, well, we don't want to have to download the entire image again, right? We don't want to have to download, obviously, the entire like JavaScript again. Now, so actually, in reality, I mean, your web browser will also cache these as well. But let's say, like hypothetically, if maybe another person on the network visits that same website, well, what they would then do is basically they would only have to download these resources from the proxy, right? They wouldn't have to go to the real web server in order to download that. So hopefully that makes sense. So let's say, files can be cached. Let's say maybe, for us, let's say, maybe at a later time. Or other users, let's say, or other users on the network. Alright, so I guess it doesn't actually have to be on the same network, because they could be from another network, but still going via the same proxy. Let's say, other users using the same proxy. I think that's fine. I mean, let's try and give an example. Right, so e.g., I don't know, image files, for a particular website. So I think we can just say that. Right, and of course, right, that's going to be based on the URL. So if you have a URL of, I don't know, google.com, right, /logo.jpg, well, then if someone else tries to go to that exact same URL, right, then of course, the proxy can then just return the actual image, rather than actually, sending the request onto that URL. Right then, I guess D, so the company uses cookies to allow users to keep items in the shopping cart. The items remain in the cart after the user closes their web browser. And we want to take one box to show the type of cookie that's used for this process. Okay, right, so if we talk, so actually here two of these don't even exist, right? So dynamic and static, I mean, really that's talking about IP addresses, that's not talking about cookies. So I guess these we can just instantly discount. Right, okay, so here, the items remain in the cart right after they close their web browser. Right, so if it's after they close their web browser, well then, yeah, that's then going to be persistent. Alright, so persistent, yeah, that's not going to be permanent. Usually they'll have some sort of expiry, right? Maybe, for example, 6 months or something. Yeah, whereas if we think session, right, so session, this means basically while your browser is open, right, so yeah, while you're using the current session. And of course, yeah, once you close that, well then that, yeah, okay, yeah, so okay, when you close it, that data is going to be lost. Okay, right, so then I guess we want to give 3 other ways that the company can use cookies. Right, so actually these questions are a bit weird. Often they'll say, and in fact, let me probably just type this. Right, so often they'll say, for example, to store login details. Although in reality, I mean, I don't think anyone would ever really store login details in their cookies, because yeah, that seems like a security vulnerability. Let's say, for example, if someone can run JavaScript right on your website, or yeah, on the website you're visiting, well then they can of course just see the cookies. Because basically with JavaScript, right, you can access their cookies. Right, therefore you could of course take those, right, you could then send it to your server, right, basically stealing their cookies. And of course if the cookies contain their login details, right, then of course, well that's going to be like a security vulnerability. Yeah, but I think, well, let's just say it anyway, because for some reason they always put it in the mark scheme. Let's say to store login details. Right, so yeah, so the user doesn't have to enter them. Enter them next time they visit the website. Alright, yeah, okay, and to be honest, now actually your browser can do this. Of course, you can click, remember my password. Although the thing is, right, that's actually the browser, I guess, I don't know, just storing it internally. That's not actually being stored in the cookies, right? That's going to be a completely different thing. Right, if we say I guess, I don't know, we can say something like user preferences. Right, let's say user preferences, I don't know, let's say e.g. language. Yeah, like sort of, probably language choice. So I guess for 3, I mean, you could mention another user preference. For example, like the color theme, right, whether they want light mode, dark mode, maybe some kind of setting, right, if, for example, there's some sort of filters, maybe that can remember, for example, their previous filters. Okay, so I think here probably another good one, we can probably say search history. Okay, well, let's say like item search history. So for example, when they then click in the search bar, right, then it will show them the previous items they searched for, right, if they want to search it again, or if they want to, search something similar, right, then that's going to be easier. I think that's going to be fine. Alright, and you could probably mention why they would do this. So let's say for the user's point of view, well, of course, that's going to be easier. They can just instantly click on a previous search, right, if they want to search that again. From the website's point of view, then potentially they could use that to recommend similar items. Although of course, really that's going to be generated on the server, rather than just on the sort of client, right, in their cookies. Right, okay, so the next one, right, cookies are stored by a web browser, and we want to give 2 other functions of a web browser. Right, so I think the obvious one is going to be making requests, then of course while receiving the sort of content from the web server that it sends back, and then just rendering that request as a web page. And when we say rendering, what that means is basically, well, converting, let's say, the text, right, into the actual physical web page that you see. Right, so of course, just sort of, okay. So basically, taking the HTML, well, the HTML, JavaScript, CSS, right, images, etc. And of course, just outputting that on the screen, right, as the actual website itself. How to write that? Let's say, maybe sending requests. I know, sending requests. Or in fact, we can probably say, well, I know, sending HTTP, or kind of HTTPS request. Let's say receiving the response, right, and rendering that response, right, as the web page to the user. I think that's fine. Right, then 2, I mean, so some of these, I mean, they might seem like minor features. Sometimes they even say like the back button, the forward button, or obviously storing user history. I guess, storing bookmarks, right, so their favorite sites. I think they even mention like the address bar, so of course, somewhere you can search, somewhere you can type in the website domain. I think let's go maybe storing bookmarks. well, yeah, okay, right. Let's say maybe allowing the user to store bookmarks, right, of their favorite websites. Yeah, I guess all websites they want to visit again as like a kind of like to remind them. Then question 6 says a weather station uses automated systems to collect and analyze data about the weather. The automated system uses sensors, and we want to give one other component that would be part of the automated system. Okay, so I think the obvious one here, we can probably just say microprocessor. Of course, that can be used, I don't know, to sort of save the data, right, to analyze the data, right, check if it's within the normal range. Right, I guess maybe you could also say actuators. Although the thing is, really, actuators are so actuators are mostly used right, in a control system. So if we actually want to sort of modify the conditions, however, I mean, we can't really modify the weather, so possibly there'd be no use for an actuator. Yeah, because we're not going to be able to, I don't know, turn on something to change the temperature, or we're not going to be able to, I don't know, like move something to change the humidity. So I think, yeah, just go with microprocessor here. It sort of makes the most sense. Then B, one sensor that is part of the automated system is a temperature sensor, and we want to give one other sensor that could be part of the automated system. Right, so here really I think you can just think about what we would really need to measure in kind of in the weather. So I guess, well, rain, of course, yeah, we want to measure that. So I think to measure how much rain, we can probably say a level sensor, right? Basically just a tube, yeah, kind of measuring how much water or, how much liquid has fallen. And possibly it would do that, I guess, maybe using like an infrared sensor. Yeah, it could do that, I don't know, using a pressure sensor, right, sort of determining the weight. Alright, so I think here we could probably say level sensor. Alright, let's say, I don't know, yeah, to detect a amount of rainfall. Alright, now, yeah, okay, so if we want others, I guess we can also say, like, what humidity sensor. Okay, now, of course, in the exam it says only one, right, although let's just try and write them here. Right, of course, yeah, humidity sensor, right, detects how much water is in the atmosphere. I guess maybe like a pressure sensor, or, yeah, alright, okay, so let's probably say air pressure, because we're not talking about pressure, like, on the ground, someone stepping on it. Yeah, I guess we're talking about the pressure of the atmosphere. Maybe you'd also want some kind of like gas, I don't know, yeah, gas sensor, for example, like oxygen, carbon dioxide, I don't know, like, yeah, nitrogen, yeah, just sort of checking the sort of atmospheric composition. Yeah, okay, right, possibly you'd want to measure the amount of the light, so determine how sunny it is, right, so like a light sensor, maybe ultraviolet, so yeah, determining like, is it, I know, kind of like dangerous for getting sunburnt or something. Yeah, determining how many like UV rays there are. Yeah, alright, possibly also you mentioned like a pH, right, so just determining whether there's acid rain, right, something like that. Yeah, and I think probably that's most of them. I mean, probably like wind as well. Alright, I think yeah, so I think one of them is called a barometer. Now, I'm not sure, I think barometer might be for pressure. Yeah, possibly it's for wind, I'm sort of not sure, to be honest. Alright, anyway, if we look at the next one, C, so an alert is sent to an employee if the weather in the weather office, if a temperature above 40 degrees is detected. And we want to explain how a temperature above 40 degrees is detected for the alert. Okay, so this is basically just a monitoring system. So what we can say is that the sensor will continually detect and send signals, right, send the temperature data right to the microprocessor. The microprocessor will then kind of compare the temperature data or the temperature value that is received from the sensor, and it will compare it with the 40 degree kind of like warning level that is pre-programmed into it. Right, if the temperature is above 40, well, then it's going to send an alert to the employee, I know, some email or something. Okay, although actually here probably not an email, because I guess they would want something like more, sort of like more immediate, right, probably some alarm, right, some, yeah, like mobile notification. Yeah, alright, and I think really that's it, because here it's not actually a control system, so we don't need, we don't need the microprocessor to send a signal to an actuator, because again, I mean, we can't really like reduce the temperature, if it's 40 degrees. Okay, right. Okay, so of course inside we can, we can like turn on the AC. However, I mean, here it's not really talking about the inside temperature, right? So it's talking about obviously the outside, right, global. Okay, so yeah, let's try and mention that. Let's say, right, the sensor will, the sensor or temperature sensor right, will continually send the temperature data to the microprocessor. Right, let's say which will compare it to the value of, I don't know, 40 degrees that has been pre-programmed into it. Right, okay, then we can say what if it's too high. So if the if the incoming alright, so I guess if the incoming temperature data is above that, or in fact, right, let's say current. If the current temperature data, from the sensor is above 40, right, let's say then the microprocessor realizes the situation is abnormal, right, and will send an alert to the employee. Alright, so I think for this, there's not really much we can write, kind of other than that. We could mention what happens when it falls below, although, I guess in this case, nothing really happens, right? So if it falls below 40, well then, of course, no alert is going to be sent. Alright, so I think here I'm going to write it just to fill up the space. Sometimes they give you the mark for saying what happens if it's above and what happens if it's below. So let's just sort of write both of these. Alright, let's say if the temperature is below 40, then I guess then nothing will happen. I think that should be okay. Right then 2, so the data for the alert is sent using serial simplex data transmission. Explain how the data is sent using serial simplex data transmission. Right, and this is going to be 3 marks. So let's say, what can we say for serial? So serial, we can say, one is sent sequentially 1 bit at a time, right, kind of in order. So the data is broken up, right, if it's in bytes. Of course, it's broken up, sent 1 bit at a time. We can also say it's sent along a single wire. And I guess for simplex, that means the data is sent in one direction only. Alright, so I guess from the microprocessor to whatever alert system is in the office, right? So maybe I don't know, to their mobile phone, maybe to some sort of screen or alarm, kind of something like that. Let's try and write that then. So let's say, alright, data is broken, broken into bits, and sent along a single wire, sequentially 1 bit at a time. Alright, 1 bit at a time. Honestly, is that kind of everything? Right, so it's broken into bits, right? Single wire, 1 bit at a time. Okay, right, and then I guess just in one direction. Alright, and maybe we should mention, obviously from the microprocessor. So let's say, from the microprocessor, to the to the alerting device. Let's give an example, right? E.g. phone, screen, maybe some sort of alarm, etc. Let's say since simplex is being used, right, the data can only travel from the microprocessor to the alerting device and not the other way around. The data can only travel from the microprocessor to the alerting device, right, and not the other way around. I think that's fine. Alright, now of course if it's in the real exam, handwriting is going to use up more space, rather than typing. That should use up, kind of all of those lines. Right, then we want to give 2 advantages to the weather station employees of using an automated weather system. Right, okay, so I guess one we can say it's going to be 24/7 monitoring. We don't need, people working there overnight. Right, let's say, the automated system can, let's say can monitor, right, 24/7. Let's say we don't need, let's say we don't need employees, working all hours, right, / on holidays, etc. Although, So to be honest, if it's a big weather station, of course that is going to be 24/7, right? Just in case, I don't know, yeah, okay, yeah. So like maybe there's some like hurricane or natural disaster. If you're talking like some like small weather station like up on some mountain, like yeah, then honestly, I mean they're probably just gonna have one employee, right? They don't have someone 24/7. Right. Okay. So another one. Yeah. Okay. So if you're talking about the advantages, say to the weather station, well, you could mention things kind of like more frequent updates. So you can have updates, every second, or yeah, okay, right. So even sort of on every millisecond or something, if you wanted. Whereas of course, if you're using a person, well, a person can't really detect the temperature, like every single millisecond, right? That's obviously too fast. However, yeah, okay, all right, and I guess you could maybe mention like more accurate readings as well, because of course a sensor can measure to, I don't know, however many decimal places, whereas I guess a human can't really do that if they're just reading off, yeah, I don't know, like reading off some kind of like mercury thermometer, for example. Yeah, so I guess you say more precision. All right. However, here we're talking about advantages to the employees. So maybe you can say what the employees can focus on, I don't know, sort of like more advanced or interesting things. Yeah, for example, I don't know, like creating weather simulations, or yeah, I don't know, like creating some report looking for patterns, rather than just doing boring things like, well, yeah, sort of like reading values off a thermometer. So let's say that, let's say right, yeah, this frees up employees, right, to work on, I don't know, yeah, maybe more, okay, yeah, or let's say more important / interesting tasks, right, e.g., I don't know, yeah, like creating weather simulations, right, let's say maybe analyzing data, right, creating weather reports, right, let's say, etc. Yeah, I think that should be fine. Then E, we want to give one disadvantage to the weather station employees of using an automated weather system. Okay, so for the employees, this is maybe a bit difficult. I mean, I guess we can probably say what they might lose their job. Yeah, let's probably say that. Right, so the employee, right, might lose their job. Right, if yeah, okay, right. So what if there's not another task that they can do instead? Yeah, let's say maybe if another maybe alternative task. Right, alternative task in the weather station, right, is not available. Yes, I know, not available instead. Yeah, I think that's fine. I mean, you could maybe mention if it breaks, right? So if the automated system breaks, then potentially the employees wouldn't have the skills required to fix that. Therefore, I guess you'd have to say, well, then they might have to go on some long training course in order to learn the engineering skills actually required to operate and fix this. So yeah, that could be another disadvantage. Now, to be honest, if you're talking about a disadvantage to the weather station, I think this one is a bit easier, because you can say, well, if the automated system breaks, well, then potentially they're going to have a time where they're not actually able to take the readings. Yeah, they're going to have like a sort of dead period where they just have no data available for that period. Also, I guess if the equipment just malfunctions slightly, so it's not completely broken, but for example it's giving a slightly wrong reading, well, then of course you're going to get like erroneous data, which in some ways is even worse, because like now all of your reports, right, all your weather predictions, your weather models, right, they're all going to be wrong, because you're sort of using you're using kind of erroneous data, sort of like without even knowing it. Right, okay, then F, so the automated weather system is upgraded and given machine learning capabilities. Machine learning is part of a branch of computer science, and we want to identify the name of this branch of computer science. Right, so I guess for all of that, right, machine learning, obviously, so machine learning, things like supervised, unsupervised learning, deep learning, neural networks, right, all, okay, yeah, so all of that is just going to be part of artificial intelligence. Yeah, I guess obviously AI, right, obviously a big buzzword. Right, then we want to explain how machine learning capabilities can be used to predict future weather. Okay, so probably what we can say is what that past data can be used, and basically based on that past data we can see like what the future weather was like. So let's say if we have, I don't know, 1 week of previous data, well, if for example we see, I don't know, yeah, the temperature was like 40, the humidity was, I don't know, like 90%. Well, when we find those situations in the past, like we can say therefore there's like a 90% chance of thunderstorms. So yeah, that's kind of what we can say by using past data and past outcomes. Right, we can then use that to predict, well, obviously, sort of, yeah, like future outcomes, right, based on the current data. Right, you can also say, I guess, yeah, so I don't know, some like sort of feedback can be used, so that if the prediction is good, well, then it will continue making similar predictions. Whereas if the prediction is bad, well, then it can try to make a different prediction in future to see if that new prediction is more accurate than the previous predictions. So it can like be continuously updating, right, continuously learning. So yeah, let's try and say that. Let's say, right, previous data and outcomes, right, can be used, right, in order to predict, I guess, predict future, future weather. Right, and I think let's give an example. Let's say, for example, right, if so let's say, right, if in the past, let's say, like, specific conditions, specific conditions resulted in, I don't know, yes, like some specific weather the next day. Right, let's say, yeah, then, right, then when we see, let's say these same / similar conditions in future, right, let's say, yeah, then the system, right, the system maybe will or might predict, right, the system might predict that, yeah, I know what, okay, right, let's say that the future weather will be the same as the sort of future weather in those past scenarios. Yeah, let's say that, right, okay, that the future weather will be the same as, yeah, I know, yeah, okay, right, let's say as the weather, or yeah, as the future weather, right, in those past scenarios. Yeah, I think that's fine. Right, then let's talk about how it can like continually adapt itself or continually learn, right, improve itself. Yeah, let's say, right, if let's say if predictions are wrong, right, let's say, right, then then the model can try to adapt its prediction in the future, right, adapt its prediction, let's say, yeah, when encountering similar scenarios in future. Right, okay, yeah, alright, so let's say if this new prediction, right, is more accurate, right, then the system will continue making similar predictions in the future. Right, let's say, yeah, hence learning, or okay, yeah, alright, yeah, so let's say maybe hence continually learning. Yeah, even as new data comes in or something. Yeah, I think that should be okay. Right then, 7. So data is sent from an employee's computer to a server. The data is correct when it's sent, but an error is detected when the data is received. Right, describe how an error can occur during data transmission. Okay, so maybe we can talk, I don't know, some sort of hardware error. Yeah, like there's some, I don't know, like broken line. You could probably mention something like interference. This could be interference from another wire. It could also be something external. Yeah, maybe, I don't know, some like electrical signals or like magnetic signals from outside. Yeah, depending on, I don't know, if you're like near a factory. Yeah, or if, I don't know, there's like some solar flare or something. Yeah, let's try and mention some of that. Okay, right, let's say, yeah, if maybe if hardware is broken, or e.g. broken wire. Right, broken wire. Right, let's say, yeah, or right, or I know, yeah, if there is some external interference. Right, let's say maybe external, maybe electronic, right, magnetic. Yeah, and okay, alright, so I guess fiber optic is also going to be light. Although, to be honest, I think fiber optic is quite insulated. It generally isn't affected by kind of outside light that much. Whereas if there's some electronic magnetic interference, right, and let's sort of give examples of these. Right, let's say e.g. I know from other nearby wires. So I guess like nearby wires, in the same tube. Maybe let's say buildings, right? Yeah, such as factories. Let's say let's say like heavy machinery. Heavy machinery. Maybe things like solar flares, right, etc. Right, and let's say I guess what this means that data could be this means that data could become corrupted. Right, e.g. bits changing their values, right, or just data lost completely. Let's say that, right, this means that data could become corrupted. Right, e.g. I know bits like flipping value. Right, let's say, right, or lost entirely. I think that's fine. Okay, right then, I think this is just the final question. Okay, so it says methods of error detection and correction can be added to make sure that errors are identified after the data is transmitted. We want to complete the statements about methods of error detection and correction and use terms from the list. Not all terms need to be used, and you should only use each term once. Alright, so as always with these questions, I think it's a good idea just to read all the possible answers first. Right, okay, so acknowledgement, right, so that can be either positive or positive or negative acknowledgement. Right, of course used here, right, for ARC, right, automatic repeat request. So if it's a positive acknowledgement, this means that the sender will send data to the receiver. If the receiver successfully receives it, then they'll send a positive acknowledgement back to the sender, just sort of telling them, like, I successfully received it. Right, therefore therefore the sender can now send the next lot of data. For example, I don't know, like packet 2 or the next sort of block of packets. Right, if we have a negative acknowledgement, what this means is the sender will send the data. Right, the receiver will then get that. If the receiver detects that there's something wrong, right, maybe it does a parity check and it's sort of detected the sort of wrong parity, well then it will then send a negative acknowledgement saying like, hey, there's been a mistake, right, resend the data. So of course if if the sender gets that negative acknowledgement, well then it will resend the data as required. If the receiver if the sender doesn't get the negative acknowledgement, then it will assume that the receiver has successfully received it, right, and the sender will then just send the next lot of packets. Then of course it will send the next lot. So hopefully that makes sense. Right, so automatic repeat. Alright, okay, actually I think usually they say request, right? Automatic repeat request, or I guess automatic repeat query, right, ARC. That's what we just mentioned, right, obviously using either positive or negative acknowledgements. Obviously, binary, just base 2, obviously bit, binary, digit, right, byte, just 8 bits. Obviously, calculation, right, so check digit, that's basically going to be the end, so it could be the end, it could be the start, alright, but basically just a digit added, or a digit, a value, right, added to some data, right, based on some calculation. So, for example, if you think, let's say books, right, ISBN, right, also credit cards, you have the check digit at the end. So that's going to be used for data entry, just kind of making sure that you've actually entered the data correctly. Because if you enter the data incorrectly, well then the calculated check digit based on the data you've entered, right, should be different to the check digit, on the real, on the sort of valid data. Alright, so checksum is basically the same. The difference really is that a check digit is just one digit. The checksum, that's going to be longer. For example, I think so let's say common checksums. If we say MD5, right, MD5 is a hashing algorithm, right, obviously checksum algorithm. That's going to be 128 bits. Actually, MD5 these days is basically considered not secure. I think because you can get like collisions, right, two things can have the same checksum. I mean that's not common, but if you try like I guess like trillions and trillions of different data, like it's possible that some of them can have the same. So I guess actually a more common one now was SHA-256, right? So here that's going to use 256 bits. And if we think, so usually in human readable form, right, that's just written as ASCII. So I guess, so 256 bits, right, we would have to divide that by 8, right, in order to get the number of ASCII characters. So I guess, is that going to be 16, possibly? Yeah, I'm sort of not sure about that. Okay, right, so whatever that is, right, 256 divided by 8, well, that's going to be the number of ASCII characters that's represented as. Alright, so okay, yeah, that's kind of the difference, that a check digit is going to be one digit, whereas obviously a checksum, I mean, that's going to be like a longer string, yeah, or like a sort of longer sequence of bits. But, yeah, okay, alright, but basically it's still the same logic, where, of course, you take the data, you do some calculation, right, then, of course, if you're talking about after transmission, well, then, of course, you're going to send the data with the checksum, right, the receiver will then take the data, they'll use the same, well, yeah, the same hashing algorithm, the same checksum algorithm, and if, yeah, okay, right, so if the checksum that they generate is equal to the checksum that you send, well, then, of course, they assume the data is not corrupted. Of course, if the checksum they generate is different to the checksum that you sent, well, then, of course, they can assume that it is or has been corrupted, and, of course, they can ask for the data to be resent. Well, of course, you're right, correct me, I think we don't need that. Right, so echo check, that's going to be, well, let's say what A is going to send to B. Right, so yeah, A sends to B, let's say, I know, let's say like ABC, right, 1, 2, 3. Right, okay. Yeah, right, so B is then just going to echo that exact same data back, again, right, ABC, 1, 2, 3. Now, if A gets the same data back, right, i.e. this ABC 1, 2, 3, as what they sent, well, then, of course, they can assume that the data has been successfully received. Right, if instead they get back ABC 1, 2, 4, well, then they can assume that, you know, maybe B has got the wrong data. All right, and yeah, okay, right, so the reason I say maybe they've got the wrong data is because actually maybe here they actually received this correctly, right, so yeah, okay, so maybe the outgoing was correct, but actually maybe the corruption occurred, you know, when B was sending back to A. All right, however, I guess because A can't be sure, well, then it's just going to resend it again regardless. Right, of course, what error? Yeah, obviously even, incorrect. Yeah, okay, and I think all of these are sort of quite obvious. Right, so if we say timeout, that's going to be used in the, well, yeah, the ARC, right, the automatic repeat request. So, for example, yeah, okay, right, the sender will send data, and if we think about positive acknowledgement, then if it doesn't receive a positive acknowledgement within, I don't know, let's say 3 seconds might be the timeout, well, then it can assume that the receiver has not received it. Alright, and then it will just send it again. And if again it doesn't receive after like 3 seconds, well, then again, of course, it will just send again. Alright, and yeah, okay, so basically, okay, yeah, so it will kind of keep retrying until it's tried a given number of times. And if the number of times it's tries basically exceeds the limit, so let's say it can try 5 times, and if it's tried 5 times, you know, without successfully receiving the positive acknowledgement, well, then it can assume that there's obviously some problem in the network, the device is offline. Right, so yeah, yeah, okay, so I guess for a positive arc, you're going to have 2 things, right? So what, okay, one is going to be the timeout, right, and then you're also going to have the retries as well. Alright, so hopefully that will make sense, and then yeah, hopefully we can now try and answer this. Right, so this one, right, a parity check is set to be, right, something or something. So honestly, like, this one is not obvious, but I think if we just look at the words, right, the only ones that could be just even or odd. Right, so a parity something is added to each byte before transmission to make it match the set parity. Right, okay, so if they're talking about, well, parity, yeah, okay, right, yeah, so if they're talking about adding to a byte, well, then that's going to be a parity bit. If you're talking about a parity block, right, yeah, okay, right, so a parity block is where you're not actually doing just for 1 byte, you're actually taking all of the bytes, right, and of course, yeah, here, okay, right, so here we have the actual parity bits for each, well, for each block, for each byte. Right, but then at the end, we also add the parity byte at the end. And of course the parity byte, well, that's then checking the kind of vertical parity. Yeah, so, okay, yeah, so hopefully that makes sense. That if we're using a parity block, right, then what we also have to add is going to be this parity byte at the end, right, and then we can check the individual parity for each of the, for each of the bytes. But then we can also check the overall kind of vertical parity. Right, and then let's say, yeah, okay, right, so let's say we got, okay, yeah, right, so let's say we get an error in, like, this column, yeah, okay, in this column, and we also get an error in this row, well, then we know that, obviously, yeah, this bit here is, you know, the bit that's sort of, like, erroneous. Alright, so the advantage of actually adding a, well, parity byte, right, if we're doing the parity block check, is that potentially we can actually find the exact bit that's become corrupted, and then obviously automatically correct that without having to actually request, you know, the resending of the data again. Alright, then if we look at the next one, so right, and something involves comparing the data sent to the data received back from the receiving device. So I think that's going to be this one here, right? We're just talking about obviously A sends to B sends to A, then obviously A just compares the data it's got back from B. Right, so that's going to be echo check. Alright, and one bit of advice I will give is that if here you just look at the grammar, right? Now, of course, because this is an, well, therefore we know that, of course, right, this next word is going to start with a vowel. Now, I guess actually, I mean, that could also be automatic repeat request or query. Alright, however, of course, this couldn't be like an parity check because, of course, well, that sort of doesn't make sense. Alright, likewise, another common tip you can look for is like sort of like plurals. So obviously, if something I don't know, maybe ends in an S, well, obviously, yes, sometimes that can like fit in like the sort of correct grammar of the sentence, whereas sometimes it can't. So often just sort of like looking at the grammar can actually, I guess, kind of whittle down some of the answers that can be. Right, and then I guess the last one. So and something uses acknowledgement and something. Right, okay. So well, that's going to be arc. I think I'm not going to write that. I'm just going to sort of draw an arrow here. It's quite a lot to write. Right, so use the acknowledgement, right, and well, timeout. The acknowledgement system can be, and again, well, that's positive, right, or negative, which we see positive, right, and negative there. Alright guys, so again, as always then, hopefully that video is useful. Any questions, ask in the comments, and I'll see you again in the next video.